Hey chemistry students, this is Mr. Dannahower, and today we're going to be learning about nuclear reactions. You're going to need to have a few resources available to you. First, in your course pack, you should find the Nuclear Reactions Notes Guide. That's going to be in the back of your Unit 1 of your course pack, so go ahead and take that out now. And that's going to look like this. If you don't have that, go ahead and get it out. The other thing that you're going to need is a periodic table. You do have a reference periodic table in your course pack. You could take that out, or you could go to the trusty periodictable.com or ptable.com, which is a great resource. As we go through the slideshow together, you should take notes of the things we talk about on your note guide, and you'll notice there are places that you can write your notes down for most of this and also to practice. Also, after you're done with the practice, you're going to need to go and fill out a form on formative for some of the problems that we completed in this session. So after you finish the notes and doing all the practice problems, you can go and complete that formative. All right, so let's talk about nuclear reactions. The first thing we want to talk about is types of change. There's three main types of changes in chemistry. One is a physical change. That usually involves just a phase of matter change, like going from a solid to a liquid, or from a solid to a gas, as we have like a sublimation. So those kinds of physical changes, or a physical change could just be something changing shape or breaking. If you broke a stick in half, it's gone through a physical change. So in chemical changes, those involve the composition of matter changing, and so now instead of just a change in shape or phase, in a chemical change we're actually rearranging the atoms or the structure of things, and we're breaking and forming bonds. So in a chemical change, we're usually changing from one substance to another, so the chemical nature changes there. In a nuclear change, we actually change the individual atom's identity themselves. And so this involves a change in the nucleus of an atom, and that's the protons and the neutrons. So in your notes guide, the subatomic particles that can change during a nuclear reaction are those in the nucleus, hence the term nuclear reactions. And so those are the protons and neutrons. So you can see again for number 2, a nuclear change involves the change in the actual elements themselves, or change in the nucleus, whereas a chemical change involves a rearranging of electrons and bonding between substances or atoms that will then result in new substances. Mass is always conserved, and so in a physical change, let's talk about how it's conserved there. If I were to take an ice cube and put it on a scale and melt it, the mass wouldn't change. As long as it's a closed system and a bunch of water doesn't evaporate, I would be able to see that the mass does not change. That's a physical change, right? In a chemical change, if we took, in this example, a couple of hydrogen atoms, you're going to notice this is a balanced reaction. So I've got 2 hydrogen atoms and 1 oxygen atom. These are both gases. And whenever you put those two together and get some energy involved, like a spark or a match, those are going to join together. They're going to bond together to form 2 water molecules. That's a chemical change because now we've taken 2 substances, hydrogen gas and oxygen gas, which have specific chemical properties, and in the chemical reaction we have formed a new substance through the bonding of those reactants the water has completely different chemical properties than the original substances. Chemical change. Now you can see here in a nuclear change, going back to the chemical change, how does that obey the law of conservation of mass? If I were to get the mass of these 2 hydrogen atoms, 4 hydrogen atoms and those 2 oxygen atoms, at the end the mass is going to be the same. I'm still going to have 2 times 2, 4 hydrogen atoms, and 2 times 1 is 2 oxygen atoms. So mass is conserved. Mass is always conserved in a nuclear reaction as well. And this is going to be the key thing that helps us understand how to do these practice problems. Notice here, this is the mass number, right? And you're inside the atom notes, you learned about mass number and atomic number, which is the number of protons. So this is protons plus neutrons, and this is the number of protons. So here you'll notice that the total mass number of the one reactant on this side is 208, and here 204 plus the 4 is 208. So mass is conserved before and after the reaction. Here we have 84 protons, and if we take the 82 plus 2, we have 84 protons. So mass is conserved, matter is conserved in all of these reactions. Okay. So there are three types of nuclear reactions that we're going to talk about. Nuclear fusion, nuclear fission, and radioactive decay. And there's three types of radioactive decay that we'll get into as well. So we'll go ahead and start with fusion. Fusion is kind of what it sounds like. If you think of the word fusion, fusing things together is like joining them and sticking them. So if you glued two things together or soldered two things together, it's like you're fusing them. So you're taking two smaller nuclei from different atoms and you're joining them together through the process of fusion. This is a huge process of energy and the main source of energy in the universe. And this is what is happening in stars. And so if you were to look at the sun right now and you could see what's going on there, there's a bunch of hydrogen and helium atoms, small atoms, and they're joining together because of a lot of energy that's in a star. And that actually gives off even more energy, and we're joining and making larger and larger and larger elements through that process of fusion. So we don't really have any natural reactions on Earth that are not man-made that can do fusion. You may have heard the term cold fusion before. If we could figure out cold fusion where we don't need a lot of energy for nuclei to join together, we'd be in business in terms of energy. We wouldn't need to worry about energy anymore because we'd have a lot of energy. But we do not have that technology yet. Let's look at an example of fusion. Here we have two light atoms. We have two hydrogen atoms. Notice they're different isotopes of atoms of hydrogen. This is hydrogen 2 and this is hydrogen 3. So two different, same element, different masses, right? Those are isotopes of each other. Now, that's not important. What's important here in fusion is that these two atoms join together. In this process, they're going to form a heavier atom, helium. And sometimes in these reactions, you're going to see this symbol. This is a neutron, and you'll notice a neutron is not a proton, so there is no atomic number. There's no number down here, but the number up here, neutrons have a mass of 1, and so we see that indicated. So if we look at, again, conservation of mass here, I have 2 plus 3 is 5. And 4 plus 1 is 5 for the mass. Mass is conserved. For my protons, sorry, I have 1 and 1 is 2, and 2 and 0 is 2. So mass is conserved. Let's look at another example together here. All right, so here it's telling us that we have a fusion reaction, and we're only going to ask you to predict one product. We would never expect you to be able to tell us how many neutrons are going to form or anything like that. So really all we're doing here is some addition and subtraction. All right, so let's come here. We know in a fusion reaction, this carbon-12 atom is going to join with this hydrogen atom and form a heavier element. So what's the mass of that new element going to be? Well, on this side, our mass of all the protons and neutrons is 12 plus 1, which is 13. And there is no other product over here, so our one product must have a mass of 13. Let's look at the protons. So carbon has 6 and hydrogen has 1. That's a total of 7 on this side. Since there's only one product, all 7 protons must be for that product. Now, how do we know what element this is? This is where you go to your periodic table. The atomic number for this element, the number of protons, is the atomic number, and we're going to go look on the periodic table and find atomic number 7. So if you find your periodic table, look at the numbers on the top, and you're going to see nitrogen, symbol N, is atomic number 7. So we're going to go ahead and write that symbol in here. And so what we've created in this fusion nuclear reaction of fusion is an isotope of nitrogen, and that's going to be nitrogen 13. All right, let's do one more of these. It's a little bit more complicated because we actually have something over here besides one product. So same thing though, we have two hydrogen atoms, they're going to join together, but in this case one of the products is a neutron. We have to take that into account. So let's look at our mass number. Total number of protons and neutrons for the mass is going to be 4 on the reactants side. That means it also has to be 4 on the product side, but we already have 1 here with that neutron. So that means that whatever is left over here must have a mass of 3, so that 3 plus 1 gives us that 4, so mass is conserved. That's the mass number of the element that's going to be formed. What's the number of protons going to be? We have 1 and 1 is 2. A neutron is not a proton, so this must have 2 protons in it. Go to your periodic table and figure out which element is atomic number 2 that has 2 protons. And if you said helium, you are correct. All right. So I want you to pause the video for a second, and I would like you to figure out the element that would be here and the element that would be here, and write the nuclide symbols. If you don't remember, that's what these symbols are called, nuclide symbols, and put those into the blanks here. Remember, you do need to go ahead and do this now because you're going to be inputting these into a worksheet that will be graded after you finish this lesson. All right, so let's talk about fission. Fission is kind of the opposite of fusion. Instead of 2 atoms, nuclei coming together and sticking, in fission we have a big, heavy, unstable nucleus that breaks apart into 2 smaller nuclei. And oftentimes they give off a bunch of neutrons in the process, all right? And so we're going to see some examples of this in just a second. Where do we see fission? We see fission in nuclear power plants. That's probably the best example that we see on Earth, is whenever we take uranium, which is mined, and actually in Colorado we mine a lot of uranium. And we put that into what we call enriched uranium rods, and those go to the nuclear power plant and they bombard it with neutrons, and that causes the uranium to split and fission to happen. And that's done in a very controlled environment. If it's not, of course, it can result in bad things like explosions, maybe thinking Chernobyl or the reactor that exploded in Japan not too long ago. So we got to have that happen in very controlled environments. This is one way that we have been able to harness nuclear energy for our purposes, and a lot of energy that's produced, especially like in Europe, is from nuclear sources like a nuclear power plant. So here's an example. We have uranium, like I was saying, uranium-235. There's other isotopes of uranium, and it's going to be bombarded by this neutron here that's coming in, right? That's what that represents. And it's going to break apart into 2 lighter elements. And in the process, it's going to give off 3 neutrons right here, which we can see right there. And it's going to give off a lot of energy. Okay, and we can harness that energy and use it. So one of the things we can see is if we add up all of the numbers here, 236 would be the total, and all the numbers here, 236 is going to be the total. Same thing down here, we should have 92 total neutrons, and if we add these protons, if we add these 2 up, we're going to get to 92 as well, so mass is conserved. All right, let's take a look at an example or two. So on number 7 on your note guide, here it's getting a little more complicated, right? And again, we're only going to ask you to fill in one thing here. So we need to take a minute and do some addition and subtraction. What's the total number of protons and neutrons on this side? If we add those up, it's 236. Which means that this side must also be 236. Don't have much room there. So if we take this 144 plus 1 plus 1 is 146, and we subtract that from the 236, we're going to get a mass number of 90 for this other element that forms in this reaction. And if we look at our protons here, we have a total of 92 on the reactant side and 54 here, so we need to subtract the 54 from the 92 to see what number is our number of protons, and that's going to be 38. Again, if we go to our periodic table, take a second and look which element has the atomic number 38. Be careful here not to make the mistake of finding atomic number 90, which is not going to be accurate. We want to make sure that we're using this for our atomic number. Remember that this is our mass number. Okay. All right, mass number is always on top. Atomic number is always on the bottom. So if you go look this up, you should see the element strontium is atomic number 38. So this is the isotope strontium-90. All right, take a second and complete the next problems. And actually down here, be careful on this one. Just want to give you a tip. You're not trying to figure out the two elements that are formed. You're trying to figure out how many neutrons are released. And instead of writing them all out like this up here, where you have neutron plus neutron plus neutron, you can just write a number right here that says how many of these neutrons are formed. So you just have to figure out how many of these neutrons, using the mass number there, is going to result in the total mass number being 240. Okay, so pause the video, do this problem here, and figure out how many neutrons for this one, and then we'll move on to some decay. So now we're going to talk about our 3 types of radioactive decay. Radioactive decay in general is when we have an unstable nucleus. So it's got too much energy, it's not the right configuration, it doesn't have the right ratio of protons to neutrons, whatever. So it's just unhappy, it's not right. And so it's going to give off something, a smaller particle, some energy, and that's going to help that nucleus relax or reconfigure so that it's more stable. So let's talk about alpha decay first. In alpha decay, the particle that's given off is basically a helium nucleus. Oops. All right, it has 2 protons and 2 neutrons, and that's the particle that's given off. And so, notice we're not really paying attention to electrons here. So electrons have to do with chemical reactions more so, because we're talking about bonding with electrons. Here we're just talking about nuclei, so we just compare about protons and neutrons. All right, so and if we ever have alpha decay, just because if we're told it's alpha decay, or if we see a helium nucleus, we know it's alpha decay. And we're always going to think helium nucleus here. So like I said, they're going to go through alpha decay because just something's not right, they're not stable. Also, just to note, in general, for the first 20 elements on the periodic table, the ratio of neutrons to protons is pretty much 1-to-1. That's not true for all of them. So, you know, if an element has 3 protons, it's probably going to have about 3 neutrons, maybe 2, maybe 4, but it's about 1-to-1. When you get up into the heavier elements, those ratios change a little bit to become more stable. All right, let's get some examples going here. Here's just a visual for you. So I've got a uranium-238 nucleus, and we saw uranium-235 just a little bit ago go through a fission reaction. In this case, we have an unstable isotope of uranium-238, and to become more stable, it's going to give off this alpha particle, which is just a helium nucleus. And in the process, it's going to create thorium as well. All right. Here's an example for us. Let's talk about this one. So we have polonium, unstable nucleus of polonium, and it's going to go through alpha decay. Now, if it says alpha decay, this is what you're looking for, right? If it doesn't tell you if it's alpha decay or beta decay, if you see a helium nucleus over here, you can assume that it's probably gone through alpha decay. Not over here. Remember, alpha decay is resulting, or a product is a helium nucleus, not a reactant. So we wouldn't see that on this side. All right, in this process, it also creates an isotope of lead, lead-204. Fun fact, lead is comes from the Latin term plumbum, so lead's a long-known element. It's discovered a very long time ago, and you might know that lead pipes used to be, or pipes from plumbing and stuff used to be made out of lead, and so that's where we get our term plumber, is from the lead that used to be used in some of those pipes and stuff. All right, let's go ahead and go on to some examples together. So here, I have an unstable nucleus of lawrencium, and all of these, it's telling you they're all going to go through alpha decay. So immediately, the first thing we can do here is go ahead and put in what we know happens is we're going to give off helium nucleus, and it's always going to be 4 and 2, always, all right? We're looking for, what's the other thing here? What's the other element when this reaction happens? So again, we got to do a little bit of math. We know that the total mass over here is 256. We need the mass over here, the total, to be 256 total. But we already have 4 protons, neutrons, right, that have been given off here. And so if we subtract that 4 away from the 256, we're going to get 252 for our mass number of this new element. Down here with our protons, lawrencium has 103. But if we take away those 2, that gives us 101 protons. Again, we need to go to the periodic table and find which element has a mass number, atomic number of 101, and that's going to be MD. That is Mendelevium. Dmitri Mendeleev was one of the most famous chemists, and he was really famous for developing kind of the very first periodic table, or one of the first periodic tables, trying to organize elements that were known based on their properties, and he did a really good job. He actually predicted elements that didn't exist, and he said when we find it, or he predicted elements that they didn't know of that we would later find, and he predicted the properties of them and where they would go in the periodic table. Just did a really good job. Okay, I want you to go ahead and go to the next one here. Keep in mind, we can always go back in and check these. Did we do our math right? This should add up to this here. Okay, 252 plus 4, 256. 101 plus 2, 103. That works out. I want you to go ahead and try the next one, and I'm going to have you pause, try it out, and come back and check your answer on that one. All right, so we had proactinium. It decays to form a helium nucleus, and atomic number 89, which is AC actinium. So if you got that one right, nice job. I want you to go ahead and do the same thing with these 3, keeping in mind that you're going to be entering some of those into that formative in just a little bit. Go ahead and pause and complete those, and then we'll move on to beta decay. Okay, in beta decay, again, we have an unstable nucleus, and in this case, a beta particle is given off. Now, this is kind of weird. A beta particle is an electron. So, if you're thinking about this, how do we get an electron that comes from the nucleus of an atom? We already know electrons aren't in the nucleus. They're all orbiting in their orbitals outside, way far away from the nucleus, having nothing to do with the interior of the atom. Yet, I'm telling you now that an electron comes through a nucleus. How is that possible, right? So, here's how. I'm going to jump ahead here. A neutron, I'm going to draw a neutron here, is sort of just a proton, positive proton, and an electron, which I'm going to draw a small and a negative sign, smushed together. And I'm simplifying this. So we have a positive proton with a tiny negative electron embedded in it, and they're like squished together. That's what a neutron is. Now, look at this, right? We know neutrons are neutral, so we have a positive and a negative kind of stuck together. And yes, they would want to attract and those kinds of things, but we're not worried about that. What that does is they neutralize each other, so we have a neutral particle. Neutrons are neutral. In beta decay, in order for this nucleus to become a little more stable, this part of the neutron essentially flies off. And so we can see that here. We give off an electron. We are left with a proton, and this other antineutrino might be given off, and we always give off some energy in the process as well. More energy than is given off in alpha decay typically. So we indicate a beta particle two different ways, either this, which is the, for electron, or the beta symbol. Either one will work when we're looking at this here. So here's an example for beta decay. We have an iodine. It tells us it goes through beta decay. Now you'll notice down here that the electron is denoted with a -1, that beta particle. And remember, we have to show that somehow, because basically one of our neutrons over here, one of these neutrons, becomes a proton. So to show that in the terms of conservation of mass, we put a -1 on the beta particle. So if we look at this, we don't change the mass at all, because essentially a proton and a neutron have a mass of 1, each of them. And when that electron goes away, it doesn't change the mass at all. So the mass of electron is insignificant, and that means that when that electron leaves, it doesn't really change the mass, okay? So 138 and 138, mass is conserved, matter is conserved. Here we have 53, but because one of these neutrons became a proton, right, the atomic number went up to 54. But this indicates with this -1 that that exchange there. And so really 54 minus the 1 here gives us 53. And so this works out. All right, let's go on to some of the practice problems. So it's telling us here we have beta decay. Because it's telling us we're going through beta decay, we can just go ahead and immediately write in that beta particle. All right. And now we're looking for, well, what's the other thing here that's formed? We can look at our mass number, 6. Like I said, the mass doesn't change, right? So it's going to be 6 here, because this is 0. Electrons don't have a mass, or it's insignificant. And here we have 2. Remember that we added a proton here. And so if we have a -1, what here would equal 2? Well, I'd have to have a 3 here. 3 plus a -1 gives me the 2. So that will make this work out. And we need to go look and see what element has an atomic number of 3 on our periodic table. And that's going to be lithium. So that's what this would look like. Matter is conserved in this process. Go ahead and do the next one. Pause for just a second. Do the next one. Come back and check your answer. Okay, so you should have gotten magnesium 24, isotope of magnesium for the next one. And of course that beta particle is shown here. Go ahead and do the same thing with these last 3. All right, let's talk about our last type of decay, gamma decay. Now in this case, in alpha and beta decay, we had an unstable nucleus and a particle was given off, either a alpha particle or beta particle. In gamma decay, a gamma ray is not a particle because it is actually it is gamma rays. Like on the electromagnetic spectrum, if you think back to like your ESS class in the electromagnetic spectrum, what are the highest energy rays? You've got X-rays and you have infrared and visible and radio. Gamma rays are the highest energy rays. They have the most energy of all the electromagnetic rays. In gamma decay, that's what's given off in the process. When that nucleus goes from being really uptight and excited and it relaxes by giving off some energy in the form of a gamma ray. So here's an example, just a picture of this, right? We have an unstable or excited nucleus of carbon 12. And in order, again, for it to stabilize or relax, it's going to give off this high energy electromagnetic radiation, a gamma ray. And that can be indicated here. Notice nothing really changes, and so we don't really write equations for gamma decay because there isn't a change in matter. It's really a change in energy overall. So we're done writing reactions because we don't write reactions for gamma decay. Let's just talk about an overview of like energy of these three different types of nuclear decay. So I'm going to start down here. Alpha particles have the least amount of energy of the three. Alpha, beta, gamma. Alpha is the least amount of energy. It can't really go very far, maybe 4 to 7 inches in the air. And a sheet of paper or the dead skin that's on the outside of your body, like that you have already there, that blocks alpha particles. So really alpha particles are not dangerous to us. The only place they would really be dangerous is if you had a very high concentration, or if you ingested something into your internal body where you don't have that dead skin to protect you. And if it was inside of you, it could actually do some damage. That energy that's released could do some damage to your internals. Why would you eat something that's radioactive, right? Well, you might not know it. You may have eaten some lettuce that was sprayed with a chemical compound that happened to have some radioactive materials in it because they weren't regulated or weren't checked, and so that can happen, and then you could eat it and not even know it. So that it wouldn't be like you'd go out and eat some rock that is going to give off alpha particles. It would be some kind of chemical that had radioactive materials in it like that. So yeah, also just some terms here during nuclear decays. There's different terms for it. So it could be called radioactivity. If something is decaying and giving off nuclear radiation, it could be radioactivity. It could be nuclear energy or electromagnetic energy, or radioactive particles. So there's lots of different terms that could be used for this. Going back to energy, beta particles are kind of in the middle. They can travel a little bit farther in open air depending on what they are. They can penetrate tissue, and so if you're near something that's giving off beta radiation, it can cause some skin burns. It can cause problems with your eyes like cataracts and those kinds of things. And so because it has higher energy, it can do more damage to us. And then the last zone, of course, is gamma rays, and like I already talked about, these are very high energy. So gamma rays can basically penetrate all the way through your body, and as they go through, they can rip apart all of your biological molecules, like your DNA, your proteins, cell membranes, that kind of stuff, and cause severe burns, internal damage to your cells and stuff, and that can lead to radiation poisoning is what that can often be termed as. They can travel a mile in the air, and so really the only way to shield against it is by using like a lead shield. Maybe if you've gone to the dentist and you've had a lead cover when you get an x-ray, that could protect you somewhat, or a very thick wall like concrete or steel could protect against gamma radiation. Now, one thing I'll mention is a lot of times if a nucleus goes through, let's say a nucleus goes through beta decay, and then that nucleus still has energy, the new nucleus, and then that might go through gamma decay, and then it might be stable, or it might have to go through another beta decay or an alpha decay. And so there's oftentimes a series of decays that happen instead of just one incident where one decay gives off one particle and it's done. There's often a long series of decays before a particle becomes stable. So, I think that's all we need to cover. We've gone through, by now you should be able to identify and describe the three different main types of nuclear reactions. You should be able to compare nuclear reactions to chemical reactions to physical reactions, and you should be able to then write equations and predict products for some of these different types of nuclear reactions that we talked about. If you have any questions, this is probably posted for you, and there are some activities activities you can go through here. Otherwise, feel free to contact your teacher and ask some more questions. Have a great day.